Hi all, I am here with my new video on chapter 9 acids and bases. Let's start. Our part 6 we will learn about ionization constants. Ionization constants of acids and bases Ka and Kb. Since acid-base reactions are equilibrium systems, we can write equilibrium constants for them. These constants give us information about the relative strengths of the acid and the base. In water solution, an acid ionizes according to the equation Ha plus H2O equal to H3O plus A minus. The stronger an acid is in water, the more ions will be produced. Therefore, the concentration of hydronium ion is a measure of the strength of the acid in water solution. K equilibrium is equal to concentration of hydronium ion multiplied by concentration of A minus ion divided by concentration of Ha multiplied by concentration of water. The equilibrium constant for this reaction is as follows. Concentration constants of acids Ka. In a dilute solution, the concentration of water is constant. Therefore, it can be absorbed into K equilibrium, yielding the constant Ka. Ka is equal to concentration of hydronium ion multiplied by concentration of A minus ion divided by concentration of Ha acid. The constant Ka is known as the ionization constant for the acid Ha. The stronger the acid, the larger is its Ka value. A strong acid ionizes completely in water. In this case, the concentration of an unionized Ha aqueous at equilibrium is nearly zero, and the value of Ka is so large that it cannot be evaluated accurately. It is the reason we cannot compare the relative strength of the first 5 acids in water solution. Stepwise ionization. Acids that are capable of donating 2 or 3 protons are called respectively diprotic and triprotic acids. Collectively, they are known as polyprotic acids. Such acids undergo a process known as stepwise ionization, in which one proton is released in each step. For example, the diprotic acid carbonic acid H2CO3 ionizes in 2 steps. In first step, H2CO3 donates a proton to H2O and converts it into SCO3 minus ion. In next step, SCO3 minus ion donates a proton to water and converts it into CO3 2 minus ion, which is carbonate ion. Each step has its own specific value written as Ka1, Ka2, etc. Value for each step is much larger than the value for succeeding step, means Ka1 is greater than Ka2, Ka2 is greater than Ka3. This means that as stepwise ionization occurs, it becomes increasingly difficult to remove a proton. Constants of bases Kb. In water solution, a base ionizes according to the equation B plus H2 equal to BH plus OH minus. The stronger a base is in water, the more hydroxide ion will be produced. Therefore, the concentration of hydroxide ion is measure of the strength of the base in water solution. The ionization constant for a base measures the strength of the base in water solution. The larger the value of Kb, the stronger the base. The expression for this constant is as follows. Kb equal to concentration of BH plus ion multiplied by concentration of hydroxide ion divided by concentration of base. Ionization constant of bases Kb. A strong base such as NaOH or KOH dissociates completely in aqueous solution. Therefore, Kb values for these bases cannot be calculated accurately. This also means that hydroxide ion in aqueous solution is the strongest base that can be present in water solution. It is impossible to compare the relative strengths of bases that are stronger than hydroxide ion in aqueous solution, such as NH2 minus in water solution. To make such a comparison, other solvent must be used. Ionizing constant of water Kw. Water is poor conductor of electricity. This poor conductivity means the presence of a small amount of ions, which arise from self-ionization of the water. When we write an equilibrium constant for this reaction, we recall that the concentration of water is a constant and can be absorbed into K equilibrium. The ionization constant for water Kw can be expressed as follows. Kw is equal to concentration of hydronium ion multiplied by concentration of hydroxide ion at 2 8298K, the value of Kw is 1 into 10 power minus 14. Concentration of ionizing constant of water, Kw. In pure water, only hydronium and hydroxide ions are produced. Therefore, they are produced in equal amounts. We can use this fact to calculate concentration of hydronium ion and hydroxide ion in pure water. If X represents concentration of hydronium ion, it must also represent concentration of hydroxide ion. So in pure water at 298 K, therefore the concentration of hydronium and hydroxide ions are each 1 into 10 power minus 7 m. Suppose another substance is dissolved in the water. The fact that Kw is a constant tells us that the product of the hydronium and hydroxide ion concentration in the water will always be 1 into 10 power minus 14 at 298 K. Of an acid and a base dissolved in water. If the substance is an acid, it will increase the hydronium ion concentration in the water. Therefore, the hydroxide ion concentration must decrease if the product is to remain at 1 into 10 power minus 14. Similarly, if the substance is a base, it will increase the hydroxide ion concentration in the water. It follows that the hydronium concentration will decrease. In our next video, we will learn about pH, pOH and hydrolysis. So please like and subscribe to watch our next video.